So, good morning. Last lecture of quantitative big imaging, and now we are going to talk really big because it's about scaling up and also how to work with big data. And it doesn't move. That's strange. Now it works. So, we have some literature on big data and also cluster computing. There is a little bit about how cluster computing is set up here at ETH, in particular at the ITET department. And that is only available on the ETH network. Then there is an introduction to some databases, and with that, and also cloud computing. Here I list Amazon AWS as one reference. There are of course more, so it's not that I'm promoting that specifically, but they have pretty developed web pages describing everything, how it works, and also all their services. There are free tiers, and there is also plenty of options to pay a lot of money if you want to run it. So today's outline, I'm going to talk not in principle, in the end I will talk a little bit image processing, but mainly it's about computer science and how to work with big computing systems, because that is an important part when you start growing your data. So the first part is about parallelism, distributed computing, and different programming models. Then we come into larger system, how to organize the computing, and also how to organize your data. And finally, some computing resources, how to actually use all this knowledge in practice. So there comes some algorithms and also some toolboxes that you can work with to achieve parallel mass computing. And we have already realized there are very many problems that we have when we work with images. So first of all, we can have really big data sets. So we have many images. It can also be that you have different data sets of different types, and possibly also you want to, in the beginning of your research, you may also want to do some exploration in the data. And for that, you need quick resources in order to get quick forward. So it could be that you have a large data set and just considering having a computer with 256 gigabytes of RAM. It's not impossible today, but they are quite costly still. And then if you have 16 cores, that is, of course, today the computer that you would put 256 gigabytes of RAM in usually have more than 16 cores, but easily to divide. You have 16 cores that would give you 16 gigabytes of RAM per image, or per CPU, sorry. And on top of that, you also need to consider that you have different drive speeds and network access that you need to think about actually as limiting factors, because the further away you come from the CPU, the slower the storage is, and that is something you also have to consider in your computations. And then comes the problem. If you have your massive data set, done your computation, and all of a sudden there is an error. Everything crashes. And then you have to either restart everything and maybe run a couple of days, which is not very fun, or you have to be able to save checkpoints in different stages of your processing. One thing that actually comes to my mind right now, I did some last-minute changes on the lecture notes. So if you downloaded your lecture notes on the PDF yesterday, there is a newer version on GitHub or on the webpage. So we have some data sets. So if you're looking at the genome scale studies with thousands of samples, that's not unusual. And you need to analyze all these in the same way. You may have dynamic experiments, some process that is flying through, and you have also hundreds of measurements like that. When you go into phenotyping, you can have really huge data sets because the biological variation requires that you really do large samples in order to have a statistical power in your investigation. That was an example here, about 328 gigabytes of data set. No, thousands of these data sets. And if you look into the medical imaging, radiologists in Switzerland produce in the order of 1 petabyte of data per year. Of course, everything is not analyzed at the same time, but that's the amount of data produced at the hospitals. When you do an explorative study, you're not, well, you are in some degree sure what you're looking for, or you have an hypothesis, but you're not really sure about the details. So you need to have a flexible framework that you can develop new and quick analysis and also be able to quickly test some hypotheses. So for these, you need a very flexible and powerful system to quick come to what you really want to ask about. So here is some example projects. We have this zebrafish full animal phenotyping. There we have thousands of samples and of these fish, and the resolution was 0.74 micrometers, and that resulted in quite large images, as you can see here, 20 to 40 gigavoxels per sample. Now, again, that is also the question which data type you use. If you are happy with 8 bits or you need floating point 32 bits, that's up to the investigation exactly what you want to do, but you can see that it quickly explodes in a lot of memory when you try to analyze this. And here is a little movie showing how to go through that fish. So these are the slices going through the fish, and there are about 1,000 of images like this. So that's a pretty massive data set. And here are some objectives that may be relevant for that investigation. If we would look at the brain at very high resolution, so say 1 micron, and then you would have, let's say, 1 cubic centimeter at 1 micron, that would be thousands of gigavoxels per sample also. And here you may want to look at how different scans, how they match with each other. You want maybe to look at the blood vessel structure, and also adding some functional MRI or histology of these samples. So here you have also, again, quite a lot of data and things that need to be correlated with each other. So we have seen this workflow, and this is something that we usually have done in the class until now. We have small workflows where we read an image, then we do some filtering, labeling, computing some histogram, and then we write the result. This works on the small scale, but if you start wanting to want to be more flexible, you want to work on a lot of data, so this is already fixed. You say, this is the file name, these are the file names, and that's it. So now if you want to instead add the flexibility, you want to play with Gaussians instead and medians and see if they compare and how they compare. Then you want to look at 3D instead of 2D. And going in towards the big data side, then you also want to you have this folder structure of many images, and you want to apply the same analysis on all images. So that would mean if you just had this script, you had to rewrite it every time you want to change something. So you need to think about ways how you can optimize that workflow. And if you have started in one approach, then it may be difficult to adjust it to scale up. So you have to think about that already in the beginning. So, okay, the first little attempt, you may have a very simple approach, but very soon, if you know that you're going to work with big data, you should think about that also in your development. So there are a couple of things that you should look into in that case. So these are the options or the details you can think about. First thing is to what degree you can chunk up your data. So is the data possible to split up, or maybe even you can, if you can put it into a streaming processing. Then also structure the code in a way that it can be easily put in a processing pipeline. And of course, when you go to larger data sets, you want to make it possible to also to work with parallel processing or even distributed execution. Topics I will come to soon. And the data format is also essential actually for this analysis, because there are data formats which are less easy to work with in a distributed manner or in chunks. So there you have to look into how you organize the data and also how you save the data. Also, if you want to distribute it, distribute your coding, then you have to look into ways how you can bundle up your code so that it can be easily reproduced and run on a different computer. And finally, very important is logging, monitoring, and fail safety. So then we come back to what I talked about last week, about having tests, making sure that your code is actually doing what it should. Logging helps you in case of a crash to at least know where it happened and possibly even why it happened. And monitoring to see how the progress is, how the load on the system is, etc. So all these things you should consider when you build up your processing framework. And these are topics from computer science. Those of you who study computer science, this is probably simple stuff, but anyway, what I'm going to talk about very quickly, briefly today is parallelism, distributed computing, resource contention, actually not so much about shared memory in direct, but then there are race conditions. You need to synchronize processing, deadlocks, and different ways of how to program. This, of course, again, like several other topics I've talked about in these lectures, is entire courses and can be PhD thesis even. And yeah, these are large topics, and of course I can't cover everything. But anyway, first thing, very simply, what is parallelism? This is an everyday task. You have two things to do, and you have to do them separate in some way. So as an example, you have two tasks. You walk for 5 minutes and you want to speak on the phone for 5 minutes. If you do it serially, very simple-minded, then you walk and then you stop and then you talk. If you want to speed up things, you walk and talk at the same time, and then you have made a gain. And that is the idea behind also the parallel programming, that you are able to execute more tasks in parallel and gain time with that. And today's computers, they are made for doing this. I mean, you probably have seen that this computer has so and so many cores, and this is exactly the idea behind it, because every core can execute a task. And if you look at the CPU load on your computer, depending on when you do things, here I actually ran a process in parallel and in series, and you can see that the area under these curves are more or less the same, but the time scale is different. So if you can execute a task in parallel, you have a clear gain. If you're really into programming and very deep stuff and want to speed up things, I really recommend this video or lecture by Scott Myers, one of the icons within C++ programming, and he tells how the CPU works and how you can actually speed up your processing by smart coding. And if you now, as an algorithm, we want to do a parallel median filter, then you can do it in different ways, but typically you want to look at, in this case, I want to know how many coins I have, and the algorithm here is you have a lot of friends or a lot of processes running, and you give each a bunch of coins, and then you make each of these friends make a histogram of their coins, and finally you can merge the histograms from each of these friends, and then you get the median out of that. So you can see here, this is the count that each friend provided, and we do the reduction where we sum them up, and then you can see the histogram of each coin, and then you can easily compute the median out of that. A problem when you run in parallel is that some resources they are limited, and limited to in the way that you can not use them at the same time, and they are much less than maybe you have processes. So memory is often limited, also files. So if you try to write on the same memory spot, then you will get into trouble. It can also be that pieces of information need to be locked in different ways. And finally, the network is also a resource that is limited. It's actually a bottleneck when you try to transfer a lot of data back and forth through the system. So these are things that you need to optimize for and make sure that they are not blocking each other somehow. So the first thing is you need to coordinate, and making it easy to work with different components. And the mutability is the problem that you want to try to write on the same spot. So actually, if two processes write on the same spot, you don't know what actually is written on that spot, because one can have started writing and the other one continues writing, and then the CPU switches back and forth, and then you, in the end, have a very uncertain value on the point. Last point is blocking. As for example, if you have a hard drive or a safe zone that you need to work on, or several safe zones actually, you need to work on, there are blocking mechanisms that says, if I go into this region, no one else is allowed to. But then you have a different region that may also be blocked in the same way. Then you can come into a situation called deadlock. Deadlock means, in principle, that you have two processes and limited resources, and one process blocks one resource and the other blocks the other one, and they mutually block each other. So they want to use the resources of the other one, but they can't. And then we come to something described as the dining philosopher's problem, where we have a number of philosophers around the table and the same number of forks, and in order to eat, each philosopher needs to have 2 forks. But if they start, everybody grab for the fork on the left side, they can't eat. And then is the question how to solve the problem that someone can eat and not everybody starve. And then they need to have some kind of agreement on when to put down the forks and see if it works. So first approach would probably be just everybody, if they can't, they put back the fork and then they grab it again. And then you're back in the same problem. So then you need to have some strategies, and that has been, this is actually a benchmark test how well parallel system is working under locked resources. One thing that is more practical is the parallel speed up and slow down actually. And again, it depends on available resources, how you implement, how you schedule things, and also the overhead of the program. And ideally, when you start using parallel resources, you should have a linear speed up. Maybe not exactly 1-to-1, but some kind of linear speed up, which is proportional to the number of cores or computing resources. However, after a while, you come to this orange line that you see that it falls off, and that is the point when there is too much conflicts or waiting times between different resources, and at some point it even falls down and goes slower. So I have implemented parallel code that actually is slower than a single core. I had 10 cores running hot. The fan on the laptop was going on, but the speed didn't come. And that was because of limited resources and conflicts, and actually that brings me back to the Scott Meyer talk, which explains what happened actually. So you have to be aware how you put together your code in order to get the speed up you expect from the cores available. Here is an example from my own coding where I did a performance test, and I was trying to identify hotspots. So I have some different tasks in my processing, and you can see in the beginning you don't see anything, but if you look at this large data size, then you can see that the purple part is very long, and that one I addressed then by introducing a parallel code. And by doing that, I got a real good gain. So this helped me then to understand how to optimize the code. So it is possible to actually, just by doing simple timing on different work blocks, you can identify where you have your hotspots and what to improve. And then there is also the theoretical speedup that describes how fast can you actually become when you introduce parallel code. And when you have your code, you have one part that is by nature sequential and one part that you can parallelize. And that one is scalable with a number of cores. Now, you can see here that the latency is 1 over the sequential part plus the part that is parallelizable. And here you can see, in my example, I had this yellow part was the serial part, or sequential part, which means I actually haven't analyzed it fully, but I believe that is mainly the file handling, that writing to disk, writing and reading to disk, and it takes time and I can't speed it up, unfortunately, unless I would have a very parallel disk system, but I don't. And then I have the other part which can be parallelized, and that one scales with the number of cores I have. So this is a guidance that is the theoretical speed up you could get, but just remembering this curve, it works a while and then at some point it breaks down. So that is just a guideline So that the blue line would be what you actually would have expected if you had linear speed up. So right now until now I have only talked about the parallel computing, assuming we are on the same computer, but there is actually also something called distributed computing, and that is when you have many computers that are connected into some kind of computational unit, and then you have new tasks. And to consider, one is actually that you have delays between the connection between the computers because they have to talk over the network. The file system can be a problem because, first of all, where do you store your data so that everybody can get what they need? And there are a lot of discussions and ways how to solve it technically. I believe most of it is solved today, but in the beginning that was actually a big problem to organize that parallel computing actually had access to the data when it was needed. And one more thing is that on a distributed system, you're not alone. There can be a system where very many share the resource because it's not efficient if only one is using that, because a single user can mostly not really load the whole system. And that's why there are many customers adding on to the system, and everybody wants their share of the processing power. And different examples of how you can think about or of tasks that you can optimize for distributed computing is assumption one: you have 10 friends, and they all know all the capitals in the world. Not a single one knows every capital, but together they know it. So if you want to know the capital of a single country, you just throw out the message, I want to know the capital of, say, Switzerland. And then you just wait to get the response. You can get many responses. You don't care. You just want to take the first one that is supposed to be right. Then you want to find out who knows the most countries, each in turn, and yell out how many countries they know, and you select the highest. So that is also kind of a histogramming thing, but anyway, there you have to do some analysis of the data afterwards because you get different results from different resources. Then you have some friends, and they have some money with them, and you want to know the total amount of money. And you ask each one of them to tell how much money they have, and then you add it together. And finally, finding the median of a coin, then you have to, as in the example I had in the beginning, then you have to create some kind of histogram and make a list, and then find the median of these. And these tasks are marked up with pluses and minuses. So some tasks, they are more useful for parallel distributed computing than others. So when you do this distributed computing, you have some challenges. One is actually the communication, that you send instructions and also data, because the question is actually where the data is stored and how much data you have to send over the network, because network transfer is an expensive task. It takes time. Fault tolerance is also, if you have distributed a computational task over, say, 1,000 computers, and 2 computers, they fail. How damaging is it to the final result? And how can you solve this by some kind of redundancy in order to make sure that you get the correct result without crashing the whole computation? And then we have the data storage. is also in principle related to sending data. Where should you have the data storage, centrally or partly locally? So it could be you can have a strategy where you send at least a part of data that each process needs to that, or each node needs, and let it work on that and then send something back again. When you work with parallel computing, you also have to think about how, which programming paradigm you want to use. And you have the classic programming languages that you learn in different courses, like C, C++, Java, MATLAB, Python, everything. They usually execute the tasks one after the other in a very given order. And data management is usually manually controlled, and also job and task scheduling is manual to some degree. The scheduling is also depending on the operating system if you do it locally. And then you have potential. Of course, as you do everything manually, you can tweak and optimize the performance for a specific task. But it can be hard to optimize for more global task. So coming back to the soup that I talked about in lecture 1. So here is an example. First you buy some vegetables on the market, then you go and buy some meat. Then you go to the kitchen and chop up the different vegetables, heat the water, and then wait until the water is boiling, and then you start adding the things one after the other. So this is a clear step-by-step recipe. Instead, you could also use a declarative approach where you more or less define different tasks, and then you more state what is the goal of what you want to do, and then the goal pulls the results from the tasks. And in this case, everything, the data is managed automatically in this system, and also the scheduling, but may not be efficient because there can be waiting times, as you can see in this example here. So you have the tasks here that you define. So buy vegetables, buy meat, wait for that one happened, and then after that you can do this one, and then you have a new task completed, and then you can see here that you have the completed tasks, and you have waiting statements. And with that, it can be that some of the tasks, they are shorter, and some tasks are longer, and then it's the task for the scheduler to identify which tasks can be executed by who and what is the most efficient way to do it. And that is something that you mostly don't involve in, but you could, for example, in these tasks, even add a little tag saying, I expect this to take this time, and that helps the scheduler afterwards to find the best way of organizing the tasks. So here is a comparison side by side, and doing the second is quite complicated for a single person, but if you want to have a team doing it, it's easier to dispatch tasks to different persons, and with that you can actually distribute your processing in that way. You could also, in the imperative way, do speed up. So you put the team on doing, all are doing the same thing, and with that you can get faster forward, and that is more or less the strategies I talked about earlier when I said parallel programming. And yeah, the declarative, then you dispatch the tasks to each one of them. So in the imperative, you optimize specific tasks, and then you can work with it well. And the other one would be actually to make many soups at the same time. So you have one person standing, doing all the things, and then you have the next one standing, do the same thing, and they should take about the same time. That's another way. And with declarative, you run everything at once, and you have each core or computer to take one task and run it. And the interesting thing is that the execution order doesn't really matter, because you have the tasks defined, and you have only the synchronization points where things need to have happened. An alternative is to work with lazy evaluation. So you don't execute things unless they are needed. So in principle, you declare your whole task. Then afterwards, you say, I want a soup. And then you go backwards and propagate the task requests, and then it only executes what is needed to do. So here's the example that we never buy any tomatoes because we don't need them in the soup. So, organization. So very important when you scale up is that you need to organize data, the code, and also data sets for parameterization. And that means you need to organize file formats, folder structures in order to make it easily parallelizable. Some languages are designed in principle for doing in-memory computation and not really going beyond the border of the computer. So that also needs to be handled. And if you started doing your basic task in Excel maybe, then transferring it to doing it in Python or MATLAB or whatever language you want to use means that you have to really rewrite a lot of things. With the help of data frames, you are relatively close to what you would do in Excel, but still it is a messy task to convert an Excel spreadsheet into a programming language. So that is maybe something you should think about also. Excel may be good for doing the first tests with a table, but when you want to scale up, it's not really useful. So, one thing when you start working with these distributed computing systems is queue computing, and that is when you have a larger computing system with many users, you have to organize how to work with these resources. So you have the resources, which is a collection of computers or processors. You have memory and storage, and you may also have resources like printers or something. I don't believe you would do too much parallel printing, but anyway, that could be some kind of limited resource that you want to make sure that it is controlled. And you also have a limited time when it's available. So that is the hardware side. Then you have some jobs. That is the tasks that you want to execute. So it could be a simulation, it could be an analysis of some kind. And they have to also define the minimal and maximal resources they need to run. And you should also in the task describe how much execution time you would need for doing it. Finally, we have the users. Those are the ones that submit these jobs. They have accounts on the computer system where they can submit the jobs. And there is also a question of fairness. You don't want a single user maybe to take the whole cluster, mostly not at least, and you want to balance the load of the resources so that everybody gets their task done within reasonable time. This can also be set up with different queues, that you have queues for short jobs, you have queues for long jobs, and they have also different priorities how you can run them. And the The cluster has some structure. So we start with the head node or login node, which is the place where you log in, and it also manages the task lists, which ones can work with it. Then you have the compute node. Those you actually usually don't see in particular. They are just drones in the background that does the work that is dispatched from the head node. Then in the head node, often there is also a scheduler that decides when to run different jobs and on what resources they can run. Of course, as you have many computers, you want them connected somehow, so networking is an important thing. And finally, you need a common storage so where everybody can access the data. And as I said before, you can also consider having local storage on each node to speed up the processing, because it's quicker to have a hard drive than sending it over the network. So I think this is a good point to make a short break, and then we continue afterwards.